In the early 1990s, a system named Alvin managed to steer an autonomous vehicle driving at normal speeds on public highways. It achieved this long before modern LiDAR and terabyte-scale training clusters were available to researchers. Inside the vehicle, the hardware was remarkably constrained. The entire physical input came from a single forward-pointed camera mounted near the rearview mirror, feeding data into an onboard computer. That camera didn't understand roads, lane lines, or trees. It only captured a low-resolution 30 by 32 grid of pixel intensities. The engineering challenge was mapping that raw array of 960 pixels directly to a physical steering command. This diagram shows the network architecture Alvin used to solve this. The bottom rectangle is the input retina, those 960 individual pixels. They connect directly to 4 hidden units in the middle layer. Those hidden units process the visual data and feed their results to a final layer of 30 output units. Each of those 30 circles corresponds to a specific steering direction, ranging from sharp left to sharp right. The grid on the right depicts exactly how the network makes a decision. This is a weight matrix. It maps the connections between the pixel inputs and one of the hidden units. A white box indicates a positive mathematical weight, pushing the network toward a specific action, while a black box is a negative weight, discouraging it. Translating a raw visual scene into a steering angle using these weights means navigating a massive space of possible mathematical combinations. Simple binary logic, rules that say, if this pixel is dark, turn left, cannot process something as highly variable as a highway. Researchers had to find a mathematical method to automatically locate the optimal set of weights. The foundation of this system begins with a single-layer neural network structure known as a perceptron. It takes a vector of real-valued inputs, calculates a linear combination against a constant weight, and applies a strict threshold. If the combined value surpasses it, it outputs a 1. If it doesn't, it outputs a -1. Geometrically, you can view a perceptron as drawing a single, straight hyperplane, a rigid line slicing through an n-dimensional space of data points. It assigns a +1 to instances lying on one side of the line and a -1 to the other. The left graph illustrates linearly separable data. With distinct positive and negative examples, the perceptron easily finds the correct boundary. But on the right, the mixed examples are not linearly separable. Here, the rule fails to converge, trapping the perceptron in an endless loop. Real-world inputs, like the noisy, overlapping pixel grids pouring in from Alvin's dashboard camera, are rarely cleanly divisible by a single straight line. To process the messiness and unpredictable variability of physical reality, the rigid binary threshold of the standard perceptron simply had to go. The network needed units capable of outputting a continuous range of values. Removing that binary threshold and allowing the network to output continuous real numbers alters the nature of the learning space. We stop looking for a perfect line and start searching for the closest mathematical approximation to our target concept. To find that approximation, we have to measure how badly the network is currently performing. We define this as error, calculated as half the squared difference between actual output and target output, summed over all training examples. Because outputs are continuous, we visualize the entire hypothesis space as a 3-dimensional bowl, where the vertical axis is total error.
Training starts at a high error coordinate. Navigating via gradient descent, we determine the steepest local slope, shown by the arrow, and step directly downward. Crucially, because the error surface is continuous, it is mathematically differentiable. We do not have to guess which way is down. We can use calculus to compute the exact direction of that downward step. Finding that direction of steepest descent requires computing the derivative of the error function with respect to every single component of the weight vector. This sequence calculates the gradient. Applying the chain rule to our error function isolates how modifying one specific weight impacts total error. In equation 6, the critical negative sign guarantees we move the weight vector to decrease the error, always stepping down the slope. Moving from the calculus back to the algorithm, we apply this derivative inside a continuous weight update loop. As seen in this pseudocode, the line calculating delta W systematically modifies the weights based on each example's error. Notice the symbol eta in that calculation. This is the learning rate, a small constant that moderates the size of each step.
If the applied step is too large, the learning network might overshoot the minimum error entirely and bounce completely out of the basin. In practice, summing the error over every single piece of data before moving is computationally expensive. Instead, we use stochastic gradient descent, updating the weights incrementally after evaluating each individual example. It dynamically carves an efficient path straight toward the optimal solution. By combining multiple unthresholded linear units and training them with this gradient descent process, a method formerly known as backpropagation, we construct multi-layer networks. These structures possess immense representational power. Let's look back at the Alvin architecture. By including those 4 hidden units between the input and output layers, the network escapes the limits of a single linear boundary. A network with a hidden layer can be configured to approximate almost any bounded continuous function. But this sheer processing power introduces a dangerous paradox. A multi-layer network has so many tunable parameters that it is perfectly capable of learning the true generalized patterns of the road. However, it also has the capacity to perfectly memorize the noise. If you let the gradient descent run for too many iterations, the model falls victim to overfitting. In early iterations, it maps the general trends, but later on, it abandons broad patterns, building overly complex decision boundaries to accommodate anomalous training data. This means the naive strategy, letting the algorithm run until the training error hits absolute zero, destroys the model. A network with zero training error has overfit so completely that it loses its ability to generalize, making it practically useless when placed on a real highway with real variables. To prevent this, we monitor performance with a separate dataset, a practice called early stopping. Here, training error drops indefinitely, but validation error eventually arcs sharply upward. That inflection point marks where generalization fails and overfitting begins. That is when you must halt training. Alvin's success reveals a defining tension in machine learning. While the calculus of gradient descent provides the path to a solution, the structural discipline of early stopping ensures that solution remains grounded in the real world.